Okay, good evening. My name's Graham Wood. I'm an architect and work in Oracle database development based in Redwood Shores. I actually work there, which is the 11th floor of the 400 building, overlooking Lake Larry. Which isn't...
Not seriously been named now.
It hasn't been named. It's informal name. There's work going on in front of the... Larry's in 500, that one there. And there's work going on in front of 500 at present. They used to have one of the old America's Cup boats outside 500 as a visitor thing, so visitors could go and have the America's Cup boat. So we think they're going to put one of the ones, not from the really recent America's Cup, but from the previous one is going in, seeing as there's 3 big pylons in the water, so it's got to be a trimaran, so not this one. I'm going to be talking about active session history, architecture and advanced usage. You've seen me present on active session history before. Show of hands. Oh, okay, that's good. Right, so I was going to say if it was most of you, then I would say, well, I'll skip through the first part of this really quickly then. But seeing as most of you haven't seen it before, I won't skip through it really quickly. Sorry, Tim, this is going to be boring for you because you've seen it many times.
It's all right.
Okay. No lawyers? No? Okay, there's nothing in this that is not announced, so it doesn't apply anyway, but we have to put it in there as part of the standard Oracle slide set. So, 2 parts to this. The first part is essentially what ASH is and how it works. The second part is some more advanced usage of active session history. Okay. So let's start with how many of you have knowingly used active session history? Sure. Okay, that's good. How many of you haven't used active session history? Okay, that's a pretty good split. So,
if you used it and not paid the licensing.
Right. So if you've used any of the Enterprise Manager performance screens, you've probably used active session history. So the top activity screen in Enterprise Manager is all driven from active session history data. Right? Active session history is kind of a little bit different to most of the rest of the diagnostic data that we have in the database. Key thing being that it's sampled data rather than accounted data. Most of the stuff that we have stats for in the database is things like counters and timers, where we're either incrementing a value or we're starting and stopping timers and adding that time into a bucket somewhere. Right? With active session history, what we're doing is sampling data, and it's a much more effective way to get very fine granularity data. So why is it there? Why is it so much better than other means of doing diagnostic analysis of a system? Well, there's three key ones. One is that it's very low overhead. So active session history, in the 10 years that it's been out in the field, I've never once heard of a customer complaining about a problem on their system that has been caused by active session history collection. Right? There's a separate background that does it, mmon Lite, and I have yet to be aware of it causing a problem on any customer side. It keeps a full history of the activity on your system, which means that if you have a problem that happens that's in the middle of the night or something, then you can always go back and look at this data rather than other diagnostic techniques such as using SQL trace, where you would have to say, right, well, the next time you're going to run that, tell me and I'll turn on trace for that module, and then we'll collect some data and then we can do the analysis. So that's a key thing, that it doesn't need you to be able to reproduce the problem, because you get data about the problem the first time it happens. Right? That's the benefit of it being always on. And the granularity of the data that it collects is very detailed. So it captures many different dimensions about every session that is active in the database. Part of the reason why it doesn't cause problems on systems is that we went into a lot of care to make sure that there weren't any locks used in the capture of and recording of this stuff. So there's never any bottleneck points, any blocking points in the code. So it's never going to stall your system. And as it turns out, it actually works very well, even if your system is very overloaded. It just kind of works, really. Right? So, as I say, it's a sampling, and what we do is we sample all of the active sessions on a system every second into an in-memory buffer. And that in-memory buffer is externalized to DBAs, whoever, as $$ active session history. $$ tables are normally just ways of looking at in-memory structures in the database kernel. This is just another one. So this one happens to be a circular buffer. So what we've got here are 3 sessions, and you can see these sessions are active for part of the time. So where there's blocks of color here, that's when these sessions are active. The rest of the time they're idle. So if you have user interaction with a system, you're likely to see that there's going to be times when the session is waiting for the user to do something. Typical client-server stuff. You're going to be waiting for the user for part of the time, actually doing work for part of the time. We've got it color-coded using the EM type colors here. So green is CPU, blue is I/O. So this session was doing some CPU at that time, then it did some I/O, then it did some CPU again. So times T1, T2, T3 are our 1-second samples, and where they intersect with sessions being active, so in the first case there, all 3 of our sessions are active. So we would have an entry in active session history for each of those three sessions. And we show here some information about the session. In fact, there's about 60 different dimensions that now go into active session history. So when we collect information about a session, we collect not only which SQL statement it is it's running, the SQL ID that's running, which object it's working on, what sort of a statement it is, what wait event, if any, it's waiting on. So in these cases where it's an I/O, it will be what table or index is that I/O against, and what SQL statement is causing that I/O. So if we were waiting for a lock, we capture not only the SQL statement that is waiting for the lock, we also have columns in active session history that tell us what the session is that is blocking this current session. Right, so you have the blocking SID, and now more recently, I think it was 11, we actually got that for cross instance as well. So if you're blocked by a session that's actually on a different instance in a rack system, we now do cross instance blocking. So that's kind of an overview of what it looks like. Right? If we then look at a bit more detail about how this is actually implemented. So we have a circular buffer. It's very similar to the way that the log buffer works in the database, in that we have a circular buffer that contains our samples. So when monlight fires up once a second to do the capture, it goes through all of the session state objects, sees which ones are active, and for for every one that is active, it writes an entry into the circular buffer.
Does that increase if you have very large SGAs, or is it fixed at 2 megabytes per
CPU? The size of it is determined by the number of CPUs that you have. And I think in 11.2 it might have been increased beyond 2 megabytes per CPU. We sized it at 2 megabytes per CPU back in 10.1. CPUs are a lot, and the idea being that the amount of work that you can generate into this thing is really determined by how many CPUs you've got, which is why it was scaled by number of CPUs. Now, each of those CPUs can do way more work than it could do 10 years ago, so we now need to have more. You can have more active sessions on the system than then, and still get away with it in terms of usage. Right. So 1 second samples get written into the circular buffer. When we take an AWR snapshot, we take 1 in 10 of those samples. Now, I mean, that's essentially, we take 10-second samples going into AWR. So it's not 1 in 10 of the entries in the samples that we take. Right. It's 10-second samples. So we take the samples from on the minute, 10 seconds, 20 seconds, 30 seconds. Right. So we downsample the samples that we've collected and store it in AWR. The idea there being that if you're looking at data in near real time, then it can actually be useful to look at the 1 second granularity information. If you're looking at something that, the batch job that took 5 hours rather than 2 hours to run overnight, having 10-second samples is fine for that. So it's the analysis of ASH data, we'll come back to it later, but it's all about having a statistically valid number of samples to look at. So you don't want to be trying to look at ones and twos of samples. If you're looking at 300 samples, it's very unlikely that you're not going to get a correct analysis of what really happened. So 1 in 10 samples or 10-second samples are written to AWR when we do an AWR snapshot. And if the circular buffer is going to fill up before it's time to do an AWR snapshot, then we'll do a preemptive flush. Just like the log writer, when it will start pushing stuff out to disk rather than having to, before it can wrap. Right? We do the same thing with the ASH buffer. Okay. We put some thought into how we actually did the write to AWR. So if there's not much data, then we'll do regular old inserts. If there's a lot of data, then we'll do direct path inserts so that there's less overhead in that. Right. So if it's a few rows, just regular inserts. If there's a lot of them, we use direct path. Okay, I said about there being no locks involved in using active session history. The reason for that is that the one single writer, which is the mmon-lite process, writes in one direction around the circular buffer, and readers go in the opposite direction. So if we're reading from active session history, we always start at the current point, the latest sample, and we read backwards. And when we get to a time that is greater than when we started, we know we've gone all the way around the buffer. Right? So we stop at that point. But that means that we never have to wait for any locks. So mmon-lite doesn't even take a lock. You just have a single writer. And if you're using VDOR active session history and DBA active SES history, we fell into the problem of being limited by 32 characters for Oracle table names. So we had to pick one word to victimize. Right? Session was the one that got it. Both of these are indexed on time. So if you're accessing them, you want to be specifying a range of times, and then it can actually drive through the index. If you're using this one, DBA hist, then you probably want to be specifying the DB ID in the instance, because that's the leading part of the index that's on that as well. Okay, the pseudocode for how it goes through and collects the data. So each of the session state objects that we look at, is it connected to the database? If it is the session active? So active means, is there currently a database call in progress? And so what we mean by active is that the client has actually requested something from the database, and we're currently working on it. Right, so there can be a session connected to the database, and the client is thinking about what they're going to enter next. Right? That isn't an active session, so it's only sessions that are doing something actually doing something in the database that get captured into active session history. This gives us a huge reduction in the volume of data that we get to capture. I very often see systems where they have thousands of connections to the database. I was looking at one yesterday which had 5,400 connections to a database instance, of which over a 1 hour period they had an average of 8 active at any point in time. Right. It's very common for us to see that. It's really bad practice, and that's a different presentation. Right? If you Google for Andrew Holdsworth connection management, there's a new video up for that one as well, which explains just why that is a really bad way of doing things. And if any of you are in London tomorrow, that's our part of our presentation tomorrow. Is the UKIP? We're doing 3 of us doing a 1-day session for UKOUG in London tomorrow. So, session is active, which means we only capture typically a small number of sessions, even if there are thousands. We then copy the data out of the session state object and then copy it again, right? Just to make sure that we've got the consistent copy of it, because $, so I say they're really just ways of looking at Oracle internal memory structures, and the code isn't stopping just because we're looking at it. Right? We don't hold any locks, so we capture the data out of the session state object once, we capture it again, and if those two are the same, we assume that that's a good copy. If they differ, then we go around once again and try it again. And if it fails a second time, then there's actually a gap in the sampling because we give up at that point. Now, in 12C, we actually have a stat that we collect which will tell us how many times we're doing that. We don't think that it's been happening very much, but we thought we might as well put a stat in there. I mean, in the testing that we've done on 12C, we haven't actually had it come up.
So you'll find out your life's work is complete rubbish.
If that was the case, then it would have been useless in all the things that I've been using it for the last 10 years. So, I don't think that's too big an issue. Yeah, we do get people who say, oh, well, so you mean because of the 1 second sampling, if I write something that runs just after the sampler every 1 second, then I can hide my program from the sampler so you'll never see it. Go on, knock yourself out, try it. We've had few people who said, oh, right, but in theory you could do that. Yeah, in theory you could. Just try and do it. Nobody has yet managed to do it. several people have been really vehement until they've tried it. And nobody has yet done it. Right, default settings. As I said, we sample once per second into memory, and we take 1 in 10 of those 1 second samples and write it to AWR. The way that we calculate the ash buffer size is there. Right, so there are a couple of other limitations on the ash buffer size, so it can't be greater than 5% of the shared pool or 2% of the SGA. Those are becoming less relevant now because SGAs are normally pretty big. Right? We're not dealing with 1 and 2 gig SGAs very often these days. The max used to be 64 and it's now 156. The note in red down there, when we first started testing this in 10G, we would find that when we were running the test systems, the ash part of AWR would just grow and grow and grow. And we looked at it, and these systems were idle most of the time. So there wasn't much the only thing that was being captured in there was M1 Lite, which by definition is active at the time that the sampler is running, because it is the sampler, right? So we decided there wasn't any point in capturing that one. We know that's running, so that's the only one that hides from the sampler. Underscore parameters. There are a number of them. The underscore ash size is the way that you can override the calculated ash size. Sampling interval, so this is how the writing into the ash buffer size, and the disk filter ratio is controlling what's written into AWR. And there's sample all, which says, oh, don't bother with only the active ones, capture the whole bunch. Right? Capture everything. We've got lots of disk space, we don't care. Don't use any of those. Right? If you do use any of those, you're likely to break much of the default operation of Enterprise Manager, for example. So Enterprise Manager assumes that the ash sampling is once per second. It assumes that the AWR filter ratio is 1 in 10. Right, so all of this stuff is there, but please don't use it. It just makes a mess of everything. Right, so the only one of the do not use ones that I've ever fiddled with is actually this one, which is the ash AWR filter ratio, and I've changed that to have it write everything into AWR because we knew that there were things that were happening for very short periods of time, and we didn't have a long enough time period to collect enough samples to get a statistically valid one with the 1 in 10 samples. So we just captured the whole lot. But we only did that in one particular case in 10 years. So these things aren't stuff that you need to be playing with all the time. So what goes in? Oh, right, ash info, right. Tells us a bit more about the operation of ash. So it has things like the oldest sample time. So the oldest sample time and the latest sample time there. Latest sample time is going to be very similar to sysdate, right? Because it's right? Why they bothered putting that one in, I have no idea. Right? They'd stopped asking me about this stuff by that stage. Right? But oldest sample time there tells you how much you've got in your ash buffer. And so, on my laptop here, if I'm running a database on this, I'm probably going to have several days in memory buffer. If I'm looking at a database at PayPal or at Amazon or something like that, they may have an hour in there, or they may have 20 minutes. Their ash buffer may not. If it's a really busy system, the ash buffer may not be long enough to have a full hour's worth of in-memory hash. And what you see in the EM top activity screen is you will see blank graph on the left-hand side. So when we look at what the graphs look like a little bit later, I'll show you what that is. But it's basically the left-hand side of the graph. There's no data there. And that's normally the indication that you're not getting a full hour in your hash buffer. Sample count is how many entries you have in the buffer, and sampler elapsed time is how long it took us to actually capture the data. So we haven't actually bothered collecting any of this data until 12C, but we now have a little bit more instrumentation about what it's doing. Yes, you can calculate the window size from that, or you could just use that one and systate. It's probably easier. Right, the number of samples and the sampler elapsed time allows you to find out how long it takes to do the sampling, which even on a system with thousands of sessions in there still isn't. We're still in microseconds for those captures. And the dropped sample count here is the ones where we've been round twice and didn't find and couldn't get a consistent copy of the session state object. Okay, so hash is really a big fact table, and there's a whole bunch of dimensions. So session ID, session serial number, user ID, right? 93 columns in it at last count. There's probably a few more by now. This was done from a 12C database, I think, so it's probably not changed too much from there. So some of the more interesting ones. SQL ID caused us problems over the years, because if you've got something like a PL SQL procedure call, then which SQL ID should we be recording? Because it can have whole levels of PL SQL and SQL calling PL SQL and vice versa. So what we decided to do was to capture the top level call, and we also and what we capture as the regular SQL ID is the lowest user level SQL. So if the user level SQL calls us some system recursive SQL, we don't capture that. So back in the days when we used to do extent allocations and things like that as part of inserting into a table, we wouldn't have followed down to doing the all the FET SQLs that were being run as sys on behalf of your session. So what we're trying to do is work out what it is the session is doing, not what is being done on behalf of the session by the system. Okay, so what else have we got in here? Oh, I guess I could look at my screen here. The PL SQL entry point and the PL SQL object number. So that gives us, if you're running a procedure that's part of a package, then PL SQL entry point and object ID would tell you which procedure it is within the package that you're running. Right, so you can track down to that. SQL plan line ID there. How many of you have used SQL Monitor? Okay, those of you who haven't, I strongly recommend using SQL Monitor. It's a great way of diagnosing SQL level performance problems and helping you to understand why SQL is performing slowly. One of the things that SQL Monitor does is it tells you which lines of the plan are actually consuming all of the resource. And it does that by looking at the SQL plan line ID there. Right. Can I Okay. So yeah, SQL plan line ID is the line in the plan. So it's something like table access full emp, or row ID access on a table after an index access. So it's that sort of level of detail. We can get a breakdown within the plan for a SQL statement of where the time is going, which is extremely helpful when it comes to trying to fix SQL problems. Okay, so spoke a little bit about SQL ID. Did I get it right? Right. We did have all sorts of problems in the early days of trying to work out which was the lowest level of user SQL. And so now we have entry levels and top level and entry level, and the current level as well. For each wait event, we have those of you who remember looking at wait events yourself. They used to be P1, P2, P3. So we have those, but we also have the names of what each one of those parameters represented. Two most important columns here are wait time and time waited. And I was expecting that to be a slide on those. So when we're capturing a wait event, by definition, the wait time is 0. Wait time is 0 when you're in a wait event. Right? You're currently still waiting for it. Time waited there is the time that event actually took to complete. Now, at the time that we're doing the sampling, we don't know what that time is. So if you think of, we're sampling this and it's doing a disk read. Well, it's currently doing the disk read, so we don't know how long the disk read took to complete. So we have to do what's called a fix-up and post-process the data when this wait event is finished. We do a fix-up on the ash entry and we write in time waited. And time waited is there so we can tell the difference between, if we're seeing that a session is continually on I/O waits, we can tell the difference between it being stuck on one I/O wait that has just disappeared off into the ether and it's been stuck on the same I/O wait for 10 seconds. The disk just never responded. Or we've actually done a different I/O every second for the last 3 minutes. Right. So in the first case, time waited would just be some huge number. If it's waited for 3 minutes, time waited is going to be 180 seconds in microseconds. If it's been doing regular I/Os, time waited is likely to be 5 milliseconds, 10 milliseconds, whatever. Right, so we can tell the difference between those. Yes, Matt?
Does that mean that the M-mod light isn't just capturing what's waiting, but also captures anything that was waiting last time?
No. We'll talk about fix-up later. That's in part 2, I think. Right. Blocking session info. So we capture information for a session that is being blocked. We capture information about the session that is actually doing the blocking. Right. And prior to 11.2, we only got the blocking session if it was in the same instance. Now we get the blocking session even if it's in a different instance of a rack. And just because a session is blocking other sessions doesn't mean it's active, right? So one of the things that we see folks getting confused by is where we have sessions being blocked by one session, and that session doesn't show up in Ash. Well, if that session isn't active, if the user who is behind that session has gone for coffee, they're not going to be active. It doesn't stop them holding resources which are blocking other sessions. They might have done the operation, they might have taken out the lock that is blocking the other sessions half an hour ago. If they didn't commit, that lock isn't going to go away. Now, if it is a real user who's gone for coffee, then hopefully when they come back from their coffee, they will either commit or roll back, and then everybody will carry on. But the more common one that we see, or that gets raised to us, is where you've actually leaked a session. So some programmatic bug has meant that the session is now no longer accessible from the Java code. And what happens then, if the most typical example is that you hit some error somewhere in the Java and it jumps out of the part of the Java where it was dealing with the connection. Now, Java programmers know that garbage collector is going to come along and clean up. Garbage collector doesn't clean up database connections. So you've got a connection from the database, you've done some work, you did part of a transaction. If you now come out of that bit of Java and release it effectively, or without releasing the session, then you've got no way of getting back to that session. So you've leaked a session. And this is why we see customers who have killer scripts. How many of you have killer scripts? Right. Okay. Killer scripts are normally there because you're programmatically leaking sessions. And that's why you get left with those dangling blocks. Things can get worse as well. So it's even worse if it does keep hold, or it releases the session back into the pool, but without doing a commit or a rollback. So it's a partial transaction, because then the next session that comes along already has this partial transaction there. It's going to do whatever it was wanting to do, and then it's going to commit, including that partial transaction. That's called corrupting a database. Yeah. So that's, yeah. You have to be a little wary about those things. Object information. Object information is populated for events for which objects are relevant. Now, that includes I/O events, cluster events, row locks, buffer busy. But the object events aren't cleared when the event is finished. So you have to be wary if you're looking directly into Ash yourselves about using object IDs unless you're using a weight class for which, unless it's part of a weight class for which the object IDs are valid. Okay. Application instrumentation, so module and action here can get passed through from the application. Gives you a very good way of breaking down which parts of the application are causing the load, causing particular SQL statements. So SAP, Oracle, ERP apps are all instrumented with module and action that make it really easy to do nice breakdowns of, well, which module is all of our load coming from? Oh, well, this module represents 50% of the load, but hold on, that's only 2% of the users. What are they doing? It's kind of a handy analysis to be able to do. Session stats really went in there in order to be able to do SQL monitor, right? So it kept some information in there that gets used as part of SQL monitoring, but the ones that are more interesting if you're getting into doing your own analysis of Ash data are how much PGA is allocated to the session and how much temp space is allocated to the session. So being able to find out, if you have a rapid growth in temp size, well, which sessions are causing it and what SQL are they doing? This kind of thing. a nice thing to know. Bit vector operations. The idea of bit vectors operations is that we can time the untimable. For something to appear in a bit vector, all that we have to do, not surprisingly, is just set a bit. So things like bind operations, right, binding is a very small code path, but if you're executing it hundreds of thousands of times, that can consume a lot of CPU. And you don't need to execute it tens of thousands of times. Right? You can just bind a new value without having to rebind to the statement. So, but it's a really short code path. So it's really not practical to put timers around it, because the cost of doing the timers would be higher than the cost of the thing that you're trying to measure. Very high intrusion. So what we do is we just set a bit when we get into the bind code, and we clear the bit when we leave the bind code. So then we can do analysis and find out, well, how much time are we spending in binding? If it's a very large number, then we say, oh, doesn't seem real, doesn't seem right, let's do a bit more investigation. But a lot of the things that are in here are stuff that is really not easy to time. And there's more coming in this area as well. I said that Ash seems to work even when the server is CPU bound. So you would think, because it's running on this 1 second timer, that you might start having problems if the system is very heavily loaded. But because of the way it works, it still seems to do reasonably well. So because it's pretty efficient, it should run in a single CPU time slice. And by the time you're running heavily loaded, then your operating system is probably doing time slicing. So it's cutting things off before they've run to completion. Right? So they're being throttled by the operating system. Right? But after it's sampled, it computes when it should run next and sleeps until that point. When it wakes up, right, so if the system is busy, it's going to sit in the run queue, and then it's going to sample again. But what happens is that it's going to, as long as the run queue is consistent, we're still going to get consistent sampling, because each time it's calculating the offset to when it should run next time, and it all just works. This brings us to another thing, which is what happens to wait events when you have CPU run queue. And what happens with wait events is that they get extended by the length of time of the run queue. So if we're doing a disk I/O, then we start the timer when we issue the disk I/O, obviously on CPU at that stage. And the blue here represents the time it actually took to do the disk read. But for us to run the timer again to finish that wait event, the Oracle code has to be running, so you have to be on the processor. So you have to have sat through your time in the run queue in order to be able to run again. So the length of time on the run queue gets added to all of the wait events. Right? So if you're on a CPU-bound system, run queue inflates all of the wait events. And if the run queue is a significant period of time, say the run queue time was 1 millisecond. If you're doing a 5 millisecond I/O, then that wait time went from 5 milliseconds to 6 milliseconds. If you were doing a latch get for which you were waiting 1 microsecond, that latch get went from 1 microsecond to 1 millisecond. Right? So there's a very big differential in the hit that you, on a per wait event basis, and the hit that you get from the run queue.
you have people having lots of trouble on virtual environments with this, because then you've got potentially a high run queue in the virtual environment, and that's only getting a slice of the physical. So surely it's going to get very hard to then start interpreting what this really means.
Yeah. In virtual environments, you brought it on yourself, I'm sorry. So seriously, anybody who is running any system that has serious performance requirements, running it on a VM is just stupid. Right? If you're doing dev and test, fine. But major systems running on VMs, it just causes way more problems than it solves. It's nice for the sysadmins, it's not so nice for...
Isn't the smoking gun of that going to be really short ways, like latches?
Well,
taking a long time.
Yeah, so that's it. That's why I was saying that, a latch wait is then taking 1,000 times longer than it was, rather than taking 20% longer, which the disk IOs were. So the typical symptom that we see of a system being CPU bound is that we see latches and mutexes up at the top of the top wait events. Right? And then people start Googling for, we're seeing shared pool latches, and we're seeing cache buffer chain latches, and right? How do we get rid of these latches? You're CPU bound. Don't try and get rid of the latches. Get rid of the fact you're CPU bound. And how do you do that? More resources, right? You need more. You're out of CPU.
All those lovely licenses you can buy as well.
Yeah, right. It's the only way you're going to make it go fast. Well, okay, maybe you tune out the things that are consuming all of the CPU at present, so you can run more transactions without having to buy more licenses. But if you're CPU bound, always tune for CPU. You can either add resources or you can reduce the CPU usage per transaction. So another of the issues that we're running into with Ash determines that you're on CPU by the fact that the session is in a database call and it's not in a wait event. Right? So it derives it deduces that you're on CPU. Now, what that actually tells it is that you're either on CPU or you're waiting for CPU. You could be in run queue. Back in 10.1, we did have some uninstrumented waits, and uninstrumented waits all came out as being CPU, and because they weren't starting a timer going into the wait event, they were doing things like a sleep call. If you're in a sleep call, so you're still active as far as the database code is concerned, but you haven't gone into a wait event, then we will capture it in Ash as being on CPU. So there it was very useful for us to be able to compare Ash data to the accounted data from the sysmetrics. So we also have CPU usage in sysmetrics, and the main performance screen in Enterprise Manager uses that. So we spend a lot of time comparing and contrasting the performance page and top activity page. And where there's a difference between those two, that's normally something that's pretty interesting. And the main performance page will actually try and quantify the run queue time that you have on the system. It will try and break down CPU wait, because it has a counted CPU, it knows how long all of the other wait classes took, and it knows the total database time, because there's a metric for that. So it actually works out if there's any difference between the total of all the wait classes plus the CPU and where the database time value is, and it puts that difference as the CPU wait time. How are we doing? Right. Okay, so what's Ash good for? Well, pretty much everything, actually. Pretty much everything. I have found over the last... I've been doing Oracle performance since, well, I was going to say since Tim was a lad, but Tim still is a lad. Right. But I've been doing it for about 25 years, and probably for most of the last 10, I've been using Ash for every major escalation that I've been involved with. It's a very, very useful data source. It does allow us to very simply break down where the database time is going on a system. Right, this whole thing, the active sessions are what contribute to the database time of a system. So we can break that down in many different dimensions, and we can do it after the fact. So it's not like you need to turn on tracing for a particular module or whatever. We have this data being captured there all the time. And it's very low overhead. Now, where we have problems with it is where people don't use it as statistical data and try and do things that they can't do with statistical data with it. And then they say, oh, well, I ran this query and it told me this, and on the basis of that, I've done something here and that hasn't worked. Well, that's probably because you got the query wrong in the first place. So, let's talk about estimating database time from Ash. Definition of database time is total time spent by user sessions, foreground sessions, in the database server, either working or waiting. And an active session is one that's currently in a database call. Average active sessions is database time over elapsed time. And we get some math. Oh, we're in an educational establishment. I can show math slides and everybody doesn't glaze over automatically. But basically, database time is sampling interval times the sum of the samples that we have for each interval. The simpler way to present it is that the number of rows in Ash, because we sample once a second, each row in Ash represents 1 second of database time. So you count up the number of rows in active session history, and that's the database time. And the way that we normally use that analysis is by grouping in some dimension. So what's our top SQL statement on this system? We group by SQL ID. What's our top session? We group by session ID. If you start playing around with changing the sampling interval, then none of this stuff works and you have to start putting extra parts into the equation. Don't do it. It's just going to make everything much, much messier. Right, so this is an example of an EM top activity screen, and this is built pretty much entirely out of active session history data. So our main graph here, which shows average active sessions, is built out of Ash data. The drill downs, when we're looking at the top SQL statements and top sessions, each of these is built out of Ash data. You can see that we can get, even at this stage, we can get pretty detailed information about what's going on. So we can tell, for example, that this SQL statement here is spending some of its time doing I/O because there's blue there. Whereas some of these others, this one is exclusively CPU, and that's scheduler waits. So the light green is scheduler waits. We can see that this session is doing a whole bunch of I/O. And from looking at this, it's very likely that this SQL is being run by this session because they both have a similar pattern. So you start recognizing patterns in these things. Right, so all of this is done by doing the various group bys. So here we're doing the group bys based on the weight class, and we're stacking them up to give our active session chart. Here we're breaking it down and looking at an individual session and grouping it by weight class. Do that. So, okay, this is sample data. How accurate is the data that we're getting? What am I doing? 5 minutes. Yeah. Not going to get to your new stuff, sorry, Tim. So this SQL statement here, we're comparing sysmetric history, which is accounted data, it's measured data, with active session history, and seeing how the two of them compare. So you can see that we're doing our average active session data. We're doing some, rather than doing count star, now we tend to use either sum 1 if we're doing the in-memory one, or sum 10 if we're doing the on-disk hash. It's just easier when you for changing those down rather than doing count stars. Oh, that doesn't sound good. That sounded like my PC is about to go out of power.
It's okay, you're about to finish.
It's a pretty good job I'm about finished, yeah. So, those are the two graphs. Right, and they look pretty close to me. Right, so Ash seems to give us a pretty accurate representation of what's happening in the system. And I was saying about comparing the performance screen and the top activity screen. So this one is top activity, which is driven from Ash. This one is the main performance screen, which is driven from the sysmetric data. And you can see they map pretty closely. The difference is this one is more spiky because we have finer granularity data. Enterprise Manager gives groups data to 15-second data points for the top activity screen, whereas we only have sysmetric data once per minute. The sysmetric data is expensive for us to capture. So we can't, as we try to go to finer and finer granularity, it gets more and more expensive. Right? So we're actually downsampling the Ash to get that, and it still gives us a better picture of what's going on than the finest sysmetric data that we have. Good. And basically, the way that you use these things is where there's big areas, then that's where the database time is going. And the informal usage model that we came up with for these is, if you're using EM to do it, is click on the big stuff. Right? That's where there's big blocks of color. That's where most of the database time is. That's where all the Ash samples are. The area under the curve is database time. The height of the curve at any point is average active sessions, which is how many values we sampled, how many sessions we sampled in that 1 second. Okay, let's skip through this. So, database time is our area under the curve. Our Ash samples are effectively histograms under that database time curve. And if we look at a 1 second interval, plug in now. Yeah, right. Okay, I think I'm about to finish. So what it shows there is some on CPU, some on I/O, some on other weights, right? And just shows the equivalent of how that is presented in the top activity screen. So that's the kind of the math behind it is actually, it's simple integrals. So if you remember, even I can remember some of my high school maths.
coming up with all these Americanisms. You're from the UK.
Yeah, sorry, my grammar school maths, right. Okay, well, this will shut down in seconds now, and I'm surprised about that because it does say that it is still plugged in. Oh. But yeah, so there's examples. I'll send the presentation to Mike, and can send that out. But essentially, looking for the top SQL, we're just grouping by SQL ID here. And the new Ash Analytics, which gives you a lot more flexibility in slicing and dicing this stuff than the top activity screen. It's called Ash Analytics because it's all based on Ash. Fine. Surprise, surprise. Okay, I better stop at that point. And I better stop. Okay. So any questions?